Hello students, in the last two sessions we discussed the concepts of magnetic effects of electric current, expressions for field strength, force in the magnetic field, magnetic circuit concepts and BH curve. In this session we will discuss magnetization cycle, hysteresis loop and hysteresis loss. We will also solve some problems for the already derived expressions. Now, we will discuss what is a magnetization cycle or hysteresis loop of a given magnetic material. Let a magnetizing force H be applied to an unmagnetized bar of iron by a solenoid. Let it be increased from 0 to maximum value and then gradually reduced to 0. It will be observed that the BH curve OAC is obtained. Let the magnetizing force be reversed by reversing the current and increased in the negative direction to a maximum value and again reduced gradually to 0. We obtain a curve CDEF. Now, magnetizing force again increased in positive direction to original maximum value and that is given by the curve FZA. This process gives a closed loop called magnetization cycle. The salient features of magnetization cycle can be observed with the help of this curve. When the magnetizing force is increased from 0 to H, a BH curve OA is obtained. If H is reduced to 0, the curve should not follow AO, but that is AC. When H is equal to 0, which comes on the y axis, that is the axis of flux density, B is not 0, but has definite value OC. This value of B is known as residual magnetism, and this property of retaining the magnetism even if the field strength is 0 is called remanence or retentivity of the material. When field strength H is reversed by reversing the current direction, that is in the negative field strength axis, the value of B is 0, that is on the x axis, for a magnetizing force that is equal to OD. This negative value of H required to cancel the residual magnetism is called coercive force. That means, here in this magnetization cycle, OD represents coercive force and OC represents residual magnetism. Next, we will see hysteresis loss. Magnetization of a material in both directions is called reversal of magnetization. During this reversal of magnetization, molecular magnets or dipoles are aligned in a particular direction in the material. For positive values of field strength, dipoles are arranged in particular direction and for negative values of field strength, dipoles are arranged in the opposite direction. In doing so, there is a friction between the molecular magnets. This reversal of magnets causes a lagging of flux density behind field strength, and it is called hysteresis. Due to hysteresis, friction between molecules occurs, which produces heat loss. This heat loss is called hysteresis loss. This hysteresis loss can be found by two methods. The first method is hysteresis loss can be found by area of hysteresis loop, and that is given by hysteresis loss WH is equal to AL multiplied with area of the loop, and its units are joules per cycle, where A is area of cross section of magnetic material, L is length of the iron core or magnetic material. In the second method, hysteresis loss can be found by Stevens law, that is given by WH is equal to eta Bm to the power of 1.6 F V watts, where Bm is the maximum flux density in the core material and its units are Tesla. Eta is called Stevens hysteresis coefficient, which depends upon the value of magnetic material. V is the volume of magnetic material in meter cube, and F is the frequency of reversal of magnetization in Hertz. Up to now, we have discussed theoretical concepts of electromagnetism. Now, we will observe some of the problems based on the formulas derived. Consider a problem, that is, if a straight conductor of 100 centimeter long carrying a current of 2500 amperes placed in a magnetic field, find the mechanical force on the conductor if flux density is 0.2 Tesla. If we see this problem, the given data is length of the conductor is 100 centimeters, which is equivalent to 0.1 meter. Current flowing through the conductor I is equal to 2500 amperes. Flux density B is equal to 0.2 Tesla, and the formula for force experienced by a current carrying conductor placed in a magnetic field F is equal to BIL sin theta. Substituting the values, we will get F is equal to 0.2 multiplied with 2500 multiplied with 0.1 multiplied with sin 90. Here theta is taken as 90 degrees, since the conductor is normal to the flux density. Therefore, the total force experienced by the conductor F is equal to 50 newtons. Now, we will see one more problem. The given problem is, if a current of 10 amperes is flowing through a straight wire, determine the force on a unit north pole placed at a distance of 0.2 meters from the axis of conductor. Now, we will see the solution. In the given problem, the current passing through the straight wire I is equal to 10 amps. The distance at which field strength to be calculated D is equal to 0.2 meters, and we know that the formula for field strength of a straight wire at a point P H is equal to I by 2 pi D. Substituting the values, I is equal to 10 amperes, D is equal to 0.2 meters, we will get the total field strength at that point is equal to 7.96 ampere turns per meter. Now we will see one more problem. The given problem is, if a current of 10 amperes is flowing through a straight wire, determine the force on a unit north pole placed at a distance of 0.2 meters from the axis of conductor. Now we will see the solution. In the given problem, the current passing through the straight wire I is equal to 10 amps. The distance at which field strength to be calculated D is equal to 0.2 meters, and we know that the formula for field strength of a straight wire at a point P H is equal to I by 2 pi D. Substituting the values, I is equal to 10 amperes, D is equal to 0.2 meters, we will get the total field strength at that point is equal to 7.96 ampere turns per meter. Now we will see the problem to find field strength of a circular coil. Suppose a wire of 2.5 meters long is bent into a circle. If the current flowing through the wire is 100 amperes, find the magnetizing force at the center of the circle. For the given problem, the total length of the wire which is bent into the circle L is equal to 2.5 meters, and the given current flowing through the circular wire is 100 amperes. Since the total length of the circle L is denoted by perimeter of the circle, that is 2 pi r, then we can find the radius of the circle r is equal to 2.5 divided by 2 pi, which is equal to 0.3979 meters. Now we know that the field strength at the center of the circle H is given by I by 2 r. Here we cannot consider theta, since at the center of the circle theta is equal to 90 degrees. Therefore, the field strength at the center of the circle H is equal to I by 2 r, which is equal to 100 by 2 into 0.3979, which gives finally the field strength is 125.66 ampere turns per meter. Consider a problem to determine the force between two parallel conductors. Given problem is, two parallel conductors are separated by a distance of 10 centimeters between their centers. Find the force in newtons per meter run between the bus bars when carrying a current of 10,000 amperes. Here the given data is, distance between two conductors is 10 centimeters, that is equal to 0.1 meters. Current through current carrying bus bars, that is I1, which is equal to I2, that is equal to 10,000 amperes, and length of the conductor is 1 meter. The force between two parallel current carrying conductors F is given by mu naught mu r I1 I2 L by 2 pi d. Now, substituting the values, mu naught, that is equal to 4 pi multiplied with the 10 power minus 7, mu r is 1 because they are spaced in the air, I1 and I2 10,000 amperes each, and L is equal to 1 meter, by 2 pi multiplied with the distance between two parallel conductors is 0.1 meter. Therefore, the force between two parallel current carrying conductors is 200 newtons per meter. Now, consider one more problem. An iron ring of 10 centimeter square cross section and 100 centimeter mean circumference has 0.2 centimeter socket in it. A flux of 1 milliweber is required in the air gap. Assuming a relative permeability of 400 for iron and leakage factor of 1.2, calculate the ampere turns required to produce the above flux. Now, if the given problem is considered, it is in the form of a steel or iron ring in which we have a socket. The width of socket is 0.2 centimeters. That means the length of the air gap is 0.2 centimeters, that is equal to 0.002 meters. The remaining part is iron part and its total length is equal to 1 meter. Now, area of this iron ring is 10 centimeter square, that is equal to 10 into 10 power minus 4 meter square, and the total flux in the air gap is 1 milliweber, and the relative permeability, that is mu r of iron, is 400, and here leakage coefficient, that is given by lambda, that is equal to 1.2. If you observe this iron ring, this is equivalent to a series magnetic circuit having two portions. One is an iron path of length 1 meter and an air gap of 0.2 centimeters. Now, to determine the total magnetomotive force, we have to find out the magnetomotive force for air gap and MMF for iron ring. Now, here the air gap flux density Bz is equal to phi z by A, that is equal to 1 multiplied with 10 power minus 3 by 10 multiplied with 10 power minus 4, that is equal to 1 Tesla. Here the field strength of the air gap Hg is given by Bz by mu naught. Substituting the values of Bz, that is equal to 1 Tesla, mu naught, that is permeability of free space, that is equal to 4 pi multiplied with 10 power minus 7 henries per meter, which gives the field strength in the air gap Hg is equal to 795774.7 ampere turns per meter. Now, MMF for air gap, that is ampere turns in the air gap, is determined by Hg multiplied with Lg, where Lg is the length of air gap, which is equal to 795747 multiplied with 0.002, which is equal to 1591.6 ampere turns. Now, we will determine magnetomotive force, that is ampere turns for iron path. Here flux in the iron path is given by leakage coefficient multiplied with air gap flux, that is equal to 1.2 multiplied with 1 milliweber, which is equal to 1.2 milliwebers or 1.2 into 10 power minus 3 webers. Here the flux density in the iron part is given by flux in the iron part divided by area of cross section, that is phi I by A, which is equal to, substituting the values of phi I, that is 1.2 multiplied with 10 power minus 3, and area of cross section, that is 10 multiplied with 10 power minus 4, which gives iron gap flux density equal to 1.2 Tesla. Now field strength in the iron part, that is Hi is equal to Bi by mu naught mu r, that is given by 2387.3 ampere turns per meter, substituting the values of Bi, mu naught and mu r. Now here ampere turns for iron part or mmf for iron part can be calculated by Hi multiplied with Li, where Hi, that is field strength in the iron part, that is 2387.3 multiplied with length of iron part, that is 1 meter, which gives ampere turns for iron path is equal to 2387.3 ampere turns. Therefore, total ampere turns required in the magnetic series circuit, that is total mmf required, is equal to mmf for air gap plus mmf for iron part, that is equal to 1591.6 plus 2387.3, which gives 3978.9 ampere turns. Here consider one more problem. In the given problem, the magnetic circuit made of iron is shown in figure. The central limb has a cross section area of 8 centimeter square, and each of the side limb has a cross section area of 4 centimeter square. Calculate the ampere turns on the central limb required to produce a flux of 1 milliweber in the central limb. The flux density of iron corresponding to flux density of 1.25 Tesla is 500 ampere turns per meter. Consider the given figure. The total central limb length is 15 centimeters and the length of each side limb is 35 centimeters each. Now, in the central limb we have a solenoid or magnetic coil is connected, and the given area of cross sections are AC, that is area of central limb, is equal to 8 into 10 power minus 4 meter square, that is equal to 8 centimeter square, and area of cross section of side limb, that is AS, is equal to 4 centimeter square, which is equal to 4 into 10 power minus 4 meter square. Here the flux in the central limb, that is phi C, is equal to 1 milliweber, that is 1 into 10 power minus 3 webers. Now, suppose we want to calculate the total mmf required for whole iron path. We have to calculate mmf in the central limb and mmf required in any of the side limb. Now, first of all we calculate mmf for central limb. Now, the flux density in the central limb, that is BC, is given by the flux in the central limb phi C divided by area of cross section in the central limb, that is AC, that is equivalent to substituting the values phi C 1 into 10 power minus 3 divided by AC 8 into 10 power minus 4, which is equal to 1.25 Tesla. Here Given that the field strength of the material corresponding to a flux density of 1.25 Tesla is 500 ampere turns per meter. Therefore, MMF required in the central limb, that is ATC, is equal to HC multiplied with LC, where LC is length of the central limb. Therefore, that is equal to 500 into 0.15 meters, that is 75 ampere turns. Now, we will calculate the MMF for any side limb. Since the flux in the side limb is half of the flux in central limb, therefore, flux in the side limb phi s is equal to phi c by 2, that is equal to 1 by 2 milliwebers, that is 0.5 into 10 power minus 3 webers. Now, side limb flux density B s is equal to side limb flux phi s divided by area of cross section of side limb A s, that is equal to 0.5 into 10 power minus 3 by 4 into 10 power minus 4, that is equal to 1.25 Tesla. Since we know that for a corresponding flux density of 1.25 Tesla, the field strength Hs is equal to 500 ampere turns per meter. Therefore, MMF of side limb, that is equal to Hs multiplied with Ls, where Ls is the length of side limb, that is equal to 500 into 0.35, which is equal to 175 ampere turns. Therefore, total ampere turns required in the parallel circuit is equal to, that is AT required for central limb ATC plus AT required in the side limb, that is ATS, which is equal to 75 plus 175. Therefore, total ampere turns required is 250 AT. In this session, we discussed about magnetization cycle, hysteresis loop and hysteresis loss. We also find methods of finding hysteresis loss. We also solved few problems. I would like to suggest you to do some more problems. Thank you.
Further clarification, contact the Additional Secretary, State Board of Technical Education and Training, 7th floor, BRKR Bhavan, Tank Bund Road, Hyderabad 500063. Fax 040 322 0546.